Okay, now what I'm going to try to do is I will cover an example which will illustrate that which will illustrate this minimum error model fitting concept. And we will do this two ways. We will first do it purely algebraically so that you see how these equations that we have derived actually correspond to the algebraic form. Okay, so these equations are in vector form, but we will see that even if we do it purely algebraically, we have corresponding results matching with each other. Okay, so what's this example illustrates? How the line fitting problem actually is related with this A alpha equals B equation, okay, or minimizing this A alpha minus B term, okay. Now let's consider that we have three equations, so M is equal to 3, so we have 3 data points, okay, but and we would like to fit the or find the best fitting line to this set of data. Okay, what are our data points? We have 3 of them. We have 0, 6, 1, 0, and 2, 0. So let me plot these data points for you. Okay, so what we have here is my X and here is my Y. I go up to 4, 5, 6 here. All right, so my data points are 0 and 6. So I have a data point here at 0. I have 1 and 0. So let's also put here 1, 2. So I have 1 and 0 over here and 2 and 0 over here. Okay. And we claim that we have a best fitting line. We don't know how that line looks like. Okay, so this is our, so this actually is F star of X, or maybe let me put this as, in this case, a different variable. Let's make this T. Okay, so this is F star of T, and that is alpha 1 times T plus alpha 2 with alpha 1, alpha 2 unknowns. Okay. What is the best fitting line? Well, that means that I want to actually have these errors over here. You see, this is E1, the first error. This is E2, the second error. And this is E3, sorry, it's going outside of the paper, E3. Okay, so we want to minimize the mean of those errors. Okay, so let me try to write down first let us write A times alpha equals B. Okay, how that looks like. How do I write this set of equations? Well, I will start with my data points. Remember, a row for each data point, right? For example, for t is equal to 0, you have basically f of t is equal to alpha 1t plus alpha 2. Okay? And I know that t is equal to 0. So this is equal to alpha 1 times 0 plus alpha 2. What is it equal to? It is equal to 6. Okay? So 0 times alpha 1 plus 1 times alpha 2 is equal to 6. So that's an equation, right? At t is equal to 1, remember these are equations that we cannot satisfy concurrently. Why? Because we have more equations than unknowns. So there is a conflict, right? So in this case, right, you have, again, alpha 1 times t, which is 1, plus alpha 2 is equal to, remember the data point is equal to 0. Okay? And finally, at t is equal to 2, I have alpha 1 t, which is 2 times alpha 1, plus alpha 2 is equal to 0. Right? This is the line equation in the left-hand side. In terms of t, I'm just putting the data point. T is equal to 0, 1, and 2. And f of t, right? Here, f of t is equal to 6. F of t is equal to 0. And f of t is equal to 0 from my data points. So I get 3 equations. Now let me put it into the matrix form. Remember, I have alpha 1 and alpha 2 as my unknown parameters. Now I have a vector on the right hand side and a matrix on the left hand side. The size of this has to be 3 by 2, and you will see why that's the case. And this is 1 by 3. Okay, let's fill in the coefficients. So from the first equation, 0 times alpha 1 times 1 times alpha 2 is equal to 6. 1 times alpha 1 and 1 times alpha 2 is equal to 0. And finally, 2 times alpha 1 plus 1 times alpha 2 is equal to 0. So you see, that's my equation over here. Okay, let me erase these dimensions from here. So that's my A times alpha is equal to B equation. Okay, now I will do 2 things. First, I will try to solve this algebraically without resorting to this matrix, and then I will calculate this generalized inverse and actually show you that we will get the same thing. Okay? Okay, so case 1, let us solve the problem algebraically without using vectors too much. Okay, so what is my error squared? So I have E squared, the total error, will be E1 squared plus E2 squared plus E3 squared. I have 3 of them, right, for each data point. Let's write each one of the errors. Okay, so E1 squared is, remember, the function's value at T1 minus what the parametric form tells us, right? So the linear form, the line equation, tells us that it has to be alpha 1 T1 plus alpha 2. Okay, so that's the difference between them. Okay, that's our error. Remember, this is 6 given by the data point. T1 is equal to 0. So I can basically write down that this is simply 6 minus, because T1 is 0, this first term goes away, so we have alpha 2 squared. Okay, what about E2 squared? Same thing. F at T2 minus alpha 1 T2 plus alpha 2 squared. Okay, This time this is 0 and this is 1. Okay, so that means 0 minus alpha 1 plus alpha 2 squared, and that is equal to alpha 1 plus alpha 2 squared. Finally, let me write E3 squared. Again, f at T3 minus alpha 1 T3 plus alpha 2 squared. Okay, T3 is equal to 2. So I have, again, 0 from f at T3 minus, I have 2 times alpha 1, 2 alpha 1 plus alpha 2 squared. Okay, so this is simply 2 alpha 1 plus alpha 2 squared. So what is my total error? Right, total squared error. Remember, this is our j of alpha, right? It's the objective function in terms of the alpha parameters. So that is the error in terms of alpha 1 and alpha 2. And what is that equal to? That is equal to 6 minus alpha 2 squared plus alpha 1 plus alpha 2 squared plus 2 alpha 1 plus alpha 2 squared. Okay, you see that this is a positive function, and it grows with alpha 1 and alpha 2. That's why it's a bowl which has a minimum somewhere. Okay, now what do we do in terms of this optimization concept? We impose the necessary conditions. Okay, so write the necessary conditions. So what does that mean? I need to take the derivative of j with respect to alpha 1, and I need to take the derivative of j with respect to alpha 2. This time I'm doing them explicitly rather than in vector form. Okay, so dE, I can also say dj, by the way, dj over d alpha 1. Remember, j is a function of alpha 1 and alpha 2. Okay, let's take the derivative with respect to alpha 1. The first term does not have any alpha 1, so it just goes away. The second term has alpha 1 in it, so it's going to be 2 times alpha 1 plus alpha 2. So 2 times the term in the parentheses times the derivative of the inside with respect to alpha 1. Okay, so that's times 1, because alpha 1's derivative with respect to alpha 1 is equal to 1. Okay, plus last term, again 2 times 2 alpha 1 plus alpha 2 times 2. Okay, so let's expand that. We have 2 alpha 1 plus 2 alpha 2 plus 8 alpha 1. So 8 alpha 1 plus 4 alpha 2. So I have how many alpha 1s? 10 alpha 1 plus 6 alpha 2 is equal to 0. Okay, so if I simplify this, it's going to be 5 alpha 1 plus 3 alpha 2 is equal to 0. Okay, so an equation in terms of alpha 1 and alpha 2. Let's also take the second necessary condition, dj alpha 1 alpha 2 d alpha 2. Let's also take that derivative. Okay, so with respect to alpha 2, now the first term also has alpha 2 in it, 2 times, right, 6 minus alpha 2 and minus 1, right, the derivative of the inside, again plus 2 times alpha 1 plus alpha 2, the derivative of the inside is equal to 1, plus 2 times 2 alpha 1 plus alpha 2, again the derivative of the inside with respect to alpha 2 is equal to 1. Let's again expand and collect the terms. First of all, each term, remember this is equated to 0, so I can simplify. There are 2's in each term, so I can simplify those. All right, so I have alpha 2 minus 6 plus alpha 1 plus alpha 2 plus 2 alpha 1 plus alpha 2 equals to 0. So what do I have? I have alpha 1, 2 alpha 1, 3 alpha 1 plus 3 alpha 2 is equal to 6. Okay. Now I will leave this. I can obviously simplify this, but just I'm going to leave it like that. Okay. So 2 equations, 2 unknowns. Okay. 2 equations with respect to 2 unknowns can be solved, right? I mean, if you solve this, let's put this into matrix form, right? Because in the second way I'm going to solve it, we will directly get this matrix equation. So I have 5, remember it's a 2 by 2 matrix times alpha 1 and alpha 2 is equal to a 2 by 1 matrix. And here I have 5, 3, 0, 5, 3, 0, and 3, 3, 6. All right. Now, how do you solve for alpha 1 and alpha 2, right? You know what to do, right? Alpha 1, alpha 2 will be equal to the inverse of this matrix, 5, 3, 3, 3, inverse times 0 and 6. Now, I want you guys to remember this equation. Okay? I will also obtain this in terms of the generalized inverse concept. Okay? So, case 2, let us use the generalized inverse result. Remember, we have done this for the general case, the matrix version, and in terms of A transpose, etc. So let us remember, we need to calculate A transpose A alpha is equal to A transpose B. Okay? Let's calculate A transpose A. So, the question is this. Do we have a correspondence between the two? Okay? Let's calculate A transpose A. Remember what A was. Okay? So, A transpose is 0, 1, 1, 1, 2, 1. Let me go back and remind you what A was. Over here, right? I'm taking the transpose of this A matrix, and also I'm going to use the B matrix over here. Okay? So A transpose A, 0, 1, 1, 1, 2, 1. This will be a 2 by 2 matrix, right? So let's see, 0 times 0 plus 1 times 1 plus 2 times 2. Okay, so that's going to make a 5 over here. 0 times 1, 0. 1 times 1, 1. 2 times 1, 2. So I have a 3 here. On the second row, right? Second row of the first matrix with the first column of the second matrix, 0 times 1, 1 times 1, 1 times 2, again another 3 here. And similarly 1 plus 1 plus 1, another 3 here. Okay, so you see A transpose A is 5, 3, 3, 3. If you look back here, it's nothing but this matrix, right? So check. Okay, so you get the same matrix. So this one is A transpose A over here. Okay, let's take a look at A transpose B matrix. Again, 0, 1, 1, 1, 2, 1 times the B, which is 6, 0, 0 from our data points. So that's going to be a 2 by 1 matrix. So that's going to be 0 times 6 plus 0, 0. So this is 0. And also 1 times 6 plus 0 times 1 plus 0 times 1. So that's going to be a 6. Okay. Again, if you look at it, it corresponds to this matrix over here, right? A transpose B. Again, check. So both corresponds to the matrices we obtained with explicit derivatives. Okay? So that means you can simply solve alpha by also calculating A transpose A inverse A transpose B times, times, no times anymore, right? Basically times B. Okay, so that is the inverse of this matrix over here. Okay. So that completes our example in this case.